the energy between two bodies can be expressed as follows. Now you can think of this as the diagram, initially think of this as the diagram that we made when talking about Einstein's special theory. In that case, this was the velocity times the time, which gave you the distance traveled in a given time. This was the movement of the observer to the time dimension of the speed of light, and the value of this was the speed of light times the difference between t, the time according to his clock, and t0, or t0, the time that the body took to get from where they were together to where the moving body had moved to here. So this represented the separation in time between the two bodies. And to remember that in order to get here, your energy was required to travel, or to accelerate to travel this distance through space, and energy was required to travel against time at the speed of light for this reduced distance. And that this represented the direct distance, which I called st, and it was this that gave you the energy. Half st squared was the energy required, and then I showed that half st squared was equal to Einstein's equation, c squared times the change in mass. Well, now that was all covered in the 4th and the 4a videos. Now I want to include potential energy, because Einstein's special theory did not have any potential energy in the calculation. A body moving away from another body does create potential energy, and you have to include potential energy if you're going to be talking about gravity. So I have to do that. But the first thing I want to do, having said this, is remind you of the Einstein diagram. This actually is a different diagram. This does not represent the passage of time, and this does not represent the travel through space. This represents the separation after a period of time. But it is perhaps I should say this represents the velocity rather than what it represented before. So this is a different diagram, but this does represent the separation in space, and this represents the separation in time. So this now represents, when a body is separated in space from another body, that represents the potential energy. In other words, depending on that separation between the two bodies and depending on their masses, you know from Newton's equation that the force between them is equal to the product of their masses times the universal gravity constant divided by the square of the distance. That is the force, and when you integrate that in order to get the energy, because energy is force times distance, when you integrate that against the distance, you get the energy, the potential energy. So this length represents in a nonlinear manner the potential energy. I won't integrate that, well perhaps I will. It gives you mg times 1 over the reciprocal, the difference between the reciprocals in space. The energy between here and here, where this is a distance r1 from the center of mass. If this were the Earth's surface and I were throwing a ball in the air, then this would be the radius of the Earth at this point, giving you the potential energy at that point. Potential energy at that point would be determined by this. So this distance represents the change in potential energy given by that equation. And this is the Earth, and the ball, or whatever it is I'm throwing in there, represents the mass of that. Now, don't worry about the equations very much. I'm not getting into the calculations, just to show the principle. And so what I want to do next is to, so I'll just take this off because it's in the way. I just wanted to show you that the space between two bodies represents the change in potential energy between the two bodies. So this represents then the potential energy. As I said, it's non-linear, meaning to say that you can't say with double the space there's twice the energy. This is the separation in time, and this represents the kinetic energy in the same way. It represents the kinetic energy due to the movement backwards through time that adds to the mass of the body and therefore to the kinetic energy. Now this then, so this is not the same diagram as before, but this gives you now just the potential energy and the kinetic energy due to time, but the kinetic energy due now to the movement is not included. So that's why it's important to understand this is not the same diagram, because before this represented the kinetic energy due to movement. Now it's now space, not velocity, that's represented there. So we now have to say, what about the kinetic energy now? Because that's all part of the energy of the system, and I believe that energy can be represented by separation. So we've got to add another dimension of this. Remember how we were adding dimensions in the last one, and so we can do that, and we can add it either to here or to here, but we must add another right-angled triangle to give us the separation due to kinetic energy, and then we'll have separation due to all the energies. So let's add it to this one, like this, the right-angled triangle, and we'll say that represents, in a non-linear manner, but according to the same calculation of linearity, this represents the kinetic energy due to normal movement in space as opposed to movement in time. And let's say, therefore, you can now consider that this body is up here. Remember, this is no longer the time dimension, it's just simply a separation. So we can move or reorientate this diagram. But this now gives you a total separation, which I call representing the energy total. So now we have the same situation we had with our space diagram before, that this squared plus this squared equals this squared plus this squared equals this squared. So this squared is equal to this squared plus this squared plus this squared. And you can now, if you wanted to, you could now break that up into 3 space dimensions. And you could say, I won't do it, but you could say that this squared is equal to this squared plus this squared plus this squared plus this squared and this squared, to give, plus this squared to give you 3 dimensions of space. So you can add a whole lot of dimensions. There's no limit of the number of dimensions you can add. We only need 1 space dimension because with gravity we're not concerned about the 3 dimensions of space. The separation between the Earth and the Moon and the Earth and the Sun is a straight line. Don't worry about the 3 dimensions of space. The space contribution to the energy in terms of potential energy is the direct line space. So now we have this, and this line, this now is a model of a 2-body system with the 2 bodies here separated by a total space and made up of space due to kinetic energy due to movement through space. This will be the contribution of separation due to the energy due to movement through time, and this is the contribution of energy due to the potential energy. And with the way my theory of gravity works this way, that energy stays constant and that distance remains absolutely constant. But these 2 can move around any way they like. And as they do that, you see the separation in space will vary, and so if I drop this, the space separation between this and the center of the Earth changes, but that's a change in this, which is accompanied, reduction in space by dropping this is accompanied by an increase in the kinetic energy. And so by keeping the Pythagoras equation is one of the equations you have to deal with, the simultaneous equations. This squared equals this squared plus this squared plus this squared. And then you add to that equations to represent a constant momentum of any bodies that move, including this. This has a constant momentum, believe it or not, in all these dimensions. And it's that constant momentum and constant energy that gives you the effect that we call gravity. So that's quite a jump, and we'll spend a lot more time on this in future videos, I'm sure.